Okay, you ready for some more? Everybody's okay? I shouldn't say everybody, I should say whatever percent. All right, we'll talk about the exam later. So we're going to continue with enzyme mechanisms. I introduced you to chymotrypsin on Friday, so we're going to continue with that and then look at quickly irreversible inhibitors as opposed to the types of inhibitors we've talked about which are reversible and what they can tell you about active site residues that are involved in catalysis. So we'll go over chymotrypsin, look at its mechanism, try to appreciate how the amino acids in the active site and their relative positions are perfectly suited to hydrolyze the peptide bond that chymotrypsin is doing. We'll talk about carboxypeptidase A, which is also a protease, but it's different. It doesn't cut within proteins. It nibbles like a Pac-Man from the C-terminus, and we'll see why it's situated to do that. TPI, which is an enzyme in glycolysis, and it is a good example of general acid-base catalysis, moving protons around. And in all these cases, we want to look at what the structure is, what the enzyme's trying to do, and how the structure that it has is well suited for the function that it wants. Again, those two words. Okay, so we want to appreciate these tricks that enzymes incorporate that allow them to function so efficiently with respect to both holding on to a substrate, having some specificity in the substrates that they're looking for, then catalyzing them, and again, trying to appreciate how the structure is enabling that to happen. All right, brief flashback to Friday, just to get you reoriented. I introduced you to chymotrypsin. So the main things that we highlighted with chymotrypsin, it's an endoprotease, and it is cleaving peptide bonds, and adjacent to the preferred cleavage site, and we'll get into this a little bit later, were bulky hydrophobic residues. So when it looks at a protein, it's not going to just simply hydrolyze every peptide bond. It is looking for peptide bonds that have phenylalanine, tyrosine, tryptophan, or leucine, some bulky hydrophobic side chain right next to the peptide bond that's going to be hydrolyzed, and we'll see why that's the case. It's the founding member of the serine protease family. I introduced this because it showed, with respect to the mechanism, when you look at it in terms of the kinetics of the product production, bless you, that we get this burst and then a steady state, and what do we say that was reflective of? It was reflective of a covalent catalytic mechanism where the enzyme was interacting with the substrate, and remember in this case they were using an ester, but chymotrypsin cuts, every time I say ester it reminds me of like one of those old shows, you know, Lady Esther. No. That the product is produced quickly, don't mind me, just listen to the science, everything else, just forget about the rest of it. So we get this acylation where the enzyme gets covalently linked, okay, and then it has to be hydrolyzed off. So that brings you back up to speed with chymotrypsin. Okay, so we talked about reversible inhibitors, either competitive or non-competitive, but now we're going to talk about irreversible inhibitors because of what they provide in terms of a tool for probing active site residues that are important. So we know that enzyme and substrate will be in equilibrium with an enzyme substrate intermediate, go to product. For the case of an irreversible inhibitor, there is an inhibitor which can initially bind, and that's non-covalent. So it's simply interacting with the enzyme, and it can come on and come off. But as soon as the enzyme starts to do something with it, catalytically, you get a covalent bond between the inhibitor and the enzyme, and that is unaffected by dilution. So this is an irreversible step. So initially it's interacting with it as if it's a substrate. It's in the active site. It then tries to do what it's going to normally do catalytically, but it gets hung up, okay? So when you have an irreversible inhibitor, for it to get, if you think about it, right, a reversible inhibitor, no matter where it binds, as long as there's no covalent link between the inhibitor and the enzyme, if you dilute it, what's going to happen? Eventually it's going to fall off, or you could chase it away, because there's no covalent link. With an irreversible inhibitor, once that enzyme becomes inactivated, you could dilute it till the cows come home and it's not going to resurrect, right? So because of that, you know a covalent bond has been formed between the inhibitor and the enzyme, and invariably that's due to the inhibitor going to the active site, looking like a pseudo-substrate, incognito. It starts to work on it, and then it realizes, whoa, you're not the right dude, and by then it's too late. All right? Okay, so DFP is one irreversible inhibitor of the serine protease family. And what happens is it has these bulky hydrophobic groups here, especially here, and the enzyme, and I can tell you now that this is the manner in which serine 195, right, the important residue in the active site of the serine proteases, or serine 195 and chymotrypsin, that there's a nucleophilic attack here on this phosphorus, right? It thinks it's a carbonyl, but it's not. It gets hooked up to it, but then it cannot hydrolyze off, right? We talked about the acylation with chymotrypsin and a normal substrate, and then it gets hydrolyzed off. With DFP, it looks like a substrate. You get covalent attack, nucleophilic attack by this serine hydroxyl group, but then it gets hung up. So if you did this experiment with radioactive DFP, you get enzyme that's irreversibly inhibited. What's going on? You then generate peptides, right, from the inhibited enzyme, and what could you do? You'd break it up into small pieces, do some Edmond sequencing, and you'll get to a point where you'll have your radioactive peptide, and as you do the Edmond sequence, you're going to come to a residue that is looking a little bit funky and it's radioactive, right? And that would tell you the residue that was chemically and covalently linked to DFP, and that would strongly suggest this residue is part of the active site. It's part of the catalytic mechanism. So when they do this with DFP, you find out that serine 195 and chymotrypsin is radioactively labeled. If you do it with another irreversible inhibitor, TPCK, you get the same phenomenon of irreversible inhibition. If the TPCK is radioactively labeled, you go ahead, you isolate the enzyme, break it up, look for a radioactive fragment, do the sequencing. You find that histidine 57 is labeled. So these irreversible inhibitors then are being used as probes for important residues in the active site. So we're going to define the catalytic triad. The catalytic triad is conserved in all serine proteases. We talked about chymotrypsin being the founding member, but it's a family of serine proteases. They all have the same mechanism, and they all have an important serine, which in the case of chymotrypsin is amino acid number 195, but that serine is an essential nucleophile, okay? It's a covalent catalytic group. Second, histidine 57, identified in the manner we just said with TPCK, and we'll see that it functions as a general acid, general base. And lastly, aspartic acid 102. Aspartic acid 102 is important for the catalytic mechanism, as you'll see, but it doesn't chemically interact with substrate, so it doesn't get radioactively labeled, but it's there to serve the function as a general base. Now, with the general base, we said that the general base can stabilize, and you'll see, something that either it transiently accepts a proton, or it stabilizes the presence of the proton on a neighbor, right? So if you have a neighbor here and you want a catalytic step to be stabilized where there's a proton here, and it doesn't really want to necessarily be there, one way that this general base could function is by taking the proton off this guy's hands. But another way is if this is a negative and this is protonated and positive, just by electrostatic stabilization it can do it, okay? So you'll see how that's the case. Okay. Oof. So first let's look, and what we're doing here is we're looking in the active site, all right? So the things here, we'll go over them, but again, we're trying to see, this is kind of a cool situation where the position and the nature of the amino acids in the active site make sense with respect to what's occurring. So this line is demarcating the active site. Around this is the rest of the protein. So chymotrypsin's grabbing its substrate, which in this case is going to be a polypeptide chain, right? So when we look, here is aspartic acid 102, and here is its side chain, right? There's the carboxyl group. Histidine 57, there's the imidazole ring. Serine 195, right? There is the hydroxyl right there. So now this is the substrate, and there's 2 R residues. What that means is the rest of the polypeptide chain, right? Either more amino terminal or more C terminal. So let's look here. This is the bond that's going to be broken. There's the carbonyl of the amide bond. There is the amide nitrogen, okay? And here is the R group that's coming off that alpha carbon. So this R is corresponding to the rest of the protein. This is what? It's phenylalanine, right? So what you have here is there's a pocket. You've got the serine, histidine, and aspartic acid. They're the catalytic guys. And they're poised to work on what fits in here, and this is a hydrophobic pocket, so what fits well into there is an R group that would be hydrophobic, right? So we'll come back to that, but that kind of explains the specificity. All right. So this hydrophobic pocket allows regions of a polypeptide chain that have a hydrophobic residue to be stabilized in this position and present that peptide bond to these side chains. Everyone follow that? All right. So there's the bond that wants to be broken. There's a hydroxyl group here, okay? And when we talked about very early in terms of talking about mechanisms where you got a nucleophilic attack, what's one of the ways that you make the nucleophile more reactive? You deprotonate it, okay? So this hydroxyl group, this oxygen would be a better nucleophile, right, if this attack is done with an oxygen anion. So it doesn't want that proton. Okay? So at this early step, it says, I'm going to be able to attack better if I get rid of the proton. Who's right next door? Histidine 57, who's perfect for taking protons on, taking protons off. So it's sitting there and it goes, I can take it off your hands, right, and help you out, but now I've got this positive charge and maybe I like it there, maybe I don't, right? So if this proton, this positive charge, is being transferred to here, maybe the imidazole ring and the histidine's being a little reluctant, and the aspartic acid is right next door. And it says, chill out, don't worry about it. If you take the proton on and you become positively charged, I'll help you out, because I have a side chain that's negatively charged, and I'll make things better for you. It'll be more favorable, okay? So these are acting in concert. I've got to attack, but I attack better if I don't have the proton. Histidine 57 says, give me the proton, You go do what you have to do. I'm going to be labored with this positive charge, which maybe I don't like that much because I'm kind of on the edge, and aspartic acid says, chill, right? Three amigos, I'll help you out. So we get a stabilization of this. So there are, when we talked about the mechanism, we said that there's an acylation and there's an enzyme, bless you, substrate intermediate that's covalent. But in between, going from this to the acyl enzyme intermediate, there's a tetrahedral intermediate. Remember we talked about that? Okay? We talked about the hydrolysis of esters and therefore amides going through a tetrahedral intermediate. So here's this tetrahedral intermediate, and we've got this bond formed now. And let's look at the stability of it. We'll come back to this, but this positive charge that has resulted from histidine acting as a general what? Base. This positive charge is stabilized here. In this tetrahedral form, this oxygen is negatively charged, right? Doesn't have a double bond. So it also turns out that this amide, which is now a backbone hydrogen, is here. This amide hydrogen is here, and what do we know that those things can do? Right? What are these dots here? Hydrogen bonds. So in that tetrahedral intermediate, which is the transition state going from substrate to this first covalent quasi-stable intermediate, because it has to be hydrolyzed, remember. It goes through that transition state, and that transition state is really well stabilized, and we'll come back to that. So then, where are we here? The first product has been released. So in the experiment we talked about, that would be the burst of PNP. If we've got a polypeptide chain and we're cutting it somewhere, right, then at this step we have cut and part of the polypeptide has been released. Where's the rest of it? A polypeptide chain, it's going to get cut right next to a hydrophobic side chain. So at that step, after step 3, half of the polypeptide chain, or one half of what was, one side of what was cut with the peptide bond has been released. The remainder of it is covalently linked to the enzyme. All right? Because of that nucleophilic attack that gave us this tetrahedral intermediate, we then hydrolyze this, and you can look at the mechanism in more detail if you want, but the important point here is to really focus on the roles being played by these side chains in terms of how they're promoting this and how they're stabilizing it. So then once we're at this point, we have this product which has been released, but now what do we have to do? At this stage, we are where we would have been in that experiment at the burst phase. But what do we have to do with the enzyme now? We have to get it back to where it was, and so we have to liberate it from the peptide that it's, the part of the polypeptide that it's still covalently linked. So now we have to hydrolyze that bond. Okay? Here is the serine. Here is the oxygen, which is bonded to that carbon. So we want to break that bond, right? We want to restore the OH group. So we're going to do that now by a hydrolysis where the water oxygen, which is here, here's the water, this oxygen is going to attack that carbon as a nucleophile. Now, what did we say would make water a better nucleophile? Deprotonating it. So, what does histidine 57 do now? In the first step, it acted as a general base by taking a proton from the hydroxyl group of serine 195. Here, it's going to take a proton off of water to make that oxygen more nucleophilic, and as a consequence of getting that proton off of water, it again gets a positive charge, and aspartic acid says, chill, I'll help you out again. You worked well as a general base, took it on yourself, I'll help you. So again, we've got this same type of a situation. We go through this second tetrahedral intermediate, and then we get simply a rearrangement, a break of that bond, and we're back to where we started. Okay? So when you look at that, in going through those steps, the slow step in each of those, okay, is going through the transition state, the tetrahedral intermediate. So when you look at that, and I just blew this up from what I just described, these tetrahedral intermediates, we've got this negative charge here, all right, and that negative charge is being stabilized through hydrogen bonds, and that is known as the oxyanion pocket. The oxyanion is the oxygen in the anion form in the tetrahedral intermediate, and it is being stabilized by two main chain hydrogens projecting into this pocket. This is stabilized, right? You're in this tetrahedral configuration. This positive charge here by histidine 57 is being stabilized. So these are all favorable, what? These electrostatic interactions are favorable enthalpy, right? So if this structure is stabilized, where we're getting favorable enthalpy, that stability is a lower energy, right? The more stable something is, the lower energy it has. The more unstable it is, the more frenetic it is. Too much coffee, as I told before, it's a higher energy. So if this transition state is stabilized, as we talked about in enzyme kinetics, that lowers what? The delta G double dagger, the activation energy. And if we lower the activation energy, what do we do to the rate? Increase, okay? So the way in which this enzyme recognizes something, does something to it, and acts as a catalyst, which we said enzymes were, right? Eventually, these bonds we talked about thermodynamically, hydrolysis will happen if a protein is just sitting in water long enough. It's just a question of how long is it going to take. The enzyme here, chymotrypsin, is a protein catalyst. It's going to speed up a reaction, and it has some specificity as to where it does it. So the specificity and the mechanism of covalent attack, formation of the products, regeneration of the enzyme, all of those things, and what you get at the outset, or at the outcome, this increased rate, it's all dictated by what? Structure. Okay. So the serine family is a protease family. They all use the same catalytic strategy. They all have an essential nucleophile or covalent catalytic group of serine. They all have an adjacent histidine, which functions during general acid-base, and they all have an aspartic acid, which functions as an electrostatic catalytic group, right? It's enhancing the nucleophilicity of serine 195, but it's doing it one step removed, right? Serine becomes a better nucleophile if it gets rid of its proton. That's taken on by histidine. That step is stabilized electrostatically with aspartic acid, okay? So those comprise what's known as the catalytic triad. And if you look at it, another way of looking at it is it's a charge relay system, right? It takes the proton off one, puts charge on that, then that charge is stabilized by somebody else. It's present in the active site of all serine proteases and some other hydrolases. It's a very good mechanism to use to hydrolyze a peptide bond or an ester bond. Go ahead and look in the notes and read about site-directed mutagenesis. Right? But basically, site-directed mutagenesis, I'll give you one example here, is where you use recombinant DNA technology to go and change an amino acid to another one to test its function. All right? If it's important for function, it's going to have a big effect on the activity. Any questions so far? Pretty clear? Somewhat clear? Okay, so serine protease family is basically broken up into two warring factions, or two, there's always that side of the family and that side of the family. So one side of the family is chymotrypsin-like. So if you look at trypsin, elastase, chymotrypsin, here, let's look at their three-dimensional structure. Chymotrypsin is in blue. This is the polypeptide backbone. Trypsin is in yellow. Elastase is in green. And here's the conserved residues, right, for the catalytic triad. Serine, histidine, aspartic acid. When you look at those, their 3D structures are nearly identical, all right? So that means that sometime in the past, they all had a common ancestor. And then as time passed, they diverged a little bit in terms of their primary structure, giving little changes in their subsequent tertiary structure. But for the most part, they're distant relatives, all right? So chymotrypsin-like is an example of divergent evolution, because when you look at the 3D structure, they all look pretty much the same. Now you got the other side of the family. These are basically I guess you could say they're the in-laws. They're kind of coming in the family, but they don't have the same blood. Yeah, I like in-laws. No, I don't. I used to. I don't anymore. Yeah, I do. All right. These are unlike chymotrypsin. So one of them would be, let's say, subtlysin. When you look at the active site has the same architecture and the same strategy for catalysis, which is an aspartic acid, a histidine, and a serine in that structure. When you look at the rest of the protein, the rest of the three-dimensional structure, right, it doesn't look anything like these guys. So how did that come about? That's viewed as an example of convergent evolution, in that somewhere in the past, something that looked completely different and may not have even been a serine protease looked completely unlike these, and through time, it stumbled on the strategy of the catalytic triad, right? It basically had a different history, a different ancestral beginning, but through time, when it acquired the enhanced capacity to cleave protein substrates through this mechanism, the rest of the protein looked like the common ancestor, which was not the common ancestor here, right? So it's converging evolution because even though it started in a different place with a different ancestor, it converged on the same mechanism, all right? Okay. So when we talk about the serine proteases, they have different specificities. So we're just going to quickly go over the structural basis for that. So here is the peptide bond that we're cleaving or hydrolyzing. The R group that imparts the specificity is on the alpha carbon just before that amide bond. So if you kind of flip that over, you can see how it would be positioned in that previous figure where we were looking at the mechanism. But this R group is conferring the specificity. So in chymotrypsin, what did we say the R group was? It prefers to cleave the peptide bond immediately after an R group, which is bulky or hydrophobic. So when you look here, this is the specificity pocket, right? It's juxtaposed just across from the catalytic residues. And what did we say that was? It was a hydrophobic pocket. It's somewhat deep, so what's going to fit in there and be stabilized well is something bulky and hydrophobic. Why? If this is hydrophobic and you don't have a lot of charges or polar groups projecting into this little pocket, they're going to interact favorably with something hydrophobic. Hydrophobic van der Waals, that's what's going to occur there. So in chymotrypsin, the specificity pocket is pretty deep and it's hydrophobic. So something like tyrosine or phenylalanine is going to fit in there, and we're going to get favorable interactions. Trypsin, the R group is positively charged, lysine or arginine. And the reason for that is it has the same general active site structure, the same catalytic triad. It has a pocket, but the pocket here has a different primary structure or different side chains there. And at the bottom of that, at the bottom of the pocket, projecting up into the pocket, is the carboxylate of an aspartic acid. So now at the bottom of the pocket, you've got a negative charge. So you're going to prefer to cleave polypeptide chains where the R group just preceding it is positively charged, right? Because that is going to stabilize that portion of the polypeptide chain in the active site. Lastly, elastase. It likes very small and neutral groups, and that's because it has a very shallow pocket with a valine and a threonine. So something like alanine or serine will fit in there. All right. So there is a structural basis for the specificity. There's a structural basis for the catalytic step. Okay, so now we're going to move on to a different protease or peptidase, which is carboxypeptidase A. So carboxypeptidase A, it's different. Carboxypeptidase A is a Pac-Man. It doesn't look, let's say, within a protein and say, I want to cleave that peptide bond because there's a favorable R group. It's simply getting on the C terminus, the carboxyl terminus, and then just hydrolyzing as it goes, right? C terminal to N terminal. Bless you. There is an important arginine, arginine 145, and you'll see how that coordinates or stabilizes that C terminal carboxylate of the substrate into the active site. There is a hydrophobic pocket that binds substrate side chains, but it doesn't discriminate. It simply means that as it's doing the Pac-Man thing, if it comes to a hydrophobic residue, it's going to go through it quicker, right? And lastly, you'll see this zinc. So the zinc here, remember when we talked about general acid-base catalysis at the very end, we said there's metal catalysis where a positively charged metal there can electrostatically stabilize. A lot of enzymes are metalloenzymes. They have metal ions in there that function in this way. They're there to help out electrostatically, so we'll see how that's the case. So here is, in brown, is the carboxypeptidase, the enzyme, and here's the active site. So you could view this as an inlet or a harbor, and in the harbor, first of all, this arginine, 145, the side chain of arginine is positively charged. Here, that carboxyl group, that is, in fact, the carboxyl group at the end of the protein. That is the C terminus. So through this electrostatic interaction, this is favorable, so it's going to basically stabilize the position of a polypeptide chain. Its most C-terminal residue is going to be right here, right? So if you look at the very end of a protein, at the C-terminus, there's the carboxyl group, there's the alpha carbon, and this is the what? That's the side chain. So there is a hydrophobic pocket here, so it prefers to bind bulky hydrophobic side chains. That will be stabilized, which means if it's stabilized, it's going to stay in there longer or more stably, lower the energy, and it's going to make the hydrolysis go faster or more efficiently. In a case where this is not hydrophobic, okay, this stabilization here is enough that it will position that most C-terminal amino acid in the active site, right? But it may be kind of on and off, right? If you've got unfavorable interactions here. But sooner or later, it'll be in there long enough for the catalysis to occur, all right? So the arginine here is basically holding down, what would it be, the nose or the tail? I guess it would be the, no. Would the C-terminus of a protein be a nose or a tail? Wrong, no. All right, in any event, an ear, it's holding the ear. So here's the peptide bond. This peptide bond now is going to be hydrolyzed. So here comes the water, right? Here's the rest of the protein. This is the most C-terminal. The water is coming in. One way you can make that more nucleophilic is to deprotonate. The other one, right, is to make this more oxygen rich, to make the carbon more electron deficient, right? So if you want to make this carbon more electron deficient, the electrons are going to be moved to the oxygen. The oxygen is now going to be an oxyanion, like we saw before, and that would be stabilized not by hydrogen bonds in the case of chymotrypsin, but in this case it's being stabilized by the zinc. All right? So the zinc is there because during a slow step here, to make that step go faster, you have to stabilize it. To stabilize it, you're forming an oxyanion, which in this case is going to be a better scenario if there's a metal ion here. If the metal ion wasn't there, if you had a zinc deficiency or whatever in a case like this, then you're going to go down because this is not going to. It is zinc here. Well, when you look at enzymes, there's some fluctuation, right? It prefers this. It can kind of use that. No way is it going to use that. What do you think the basis of that is going to be? It's going to be structural. And so then the question is this zinc, and we'll get into this a little bit more when we talk about coenzymes, but that zinc has to be there electrostatically. Its charge is going to help do what it has to do, but it has to fit, right? It has to be the right size. It can't be too big, can't be too small. It's going to be just right, okay? So in this case, we don't go through a tetrahedral intermediate. It's simply get it in there, stabilize it. It'll be more stable if there's a hydrophobic side chain here, but you don't absolutely need it. Attack that bond, hydrolyze it. That's going to happen better and be more stable if you get an oxyanion, and the zinc is going to electrostatically stabilize that. Okay, last enzyme for today, triphosphate isomerase. This enzyme is a classic, and it's a good example of a general acid-base catalyst. The upshot is you're simply moving a proton between C2 and C1, all right, during glycolysis. So dihydroxyacetone phosphate to glyceraldehyde 3-phosphate, or vice versa. Either way, there's an intermediate. The important thing really here is to look at it and see how these side chains are working as general acids or general bases. So let's say in this first step with dihydroxyacetone phosphate, you want, in this case, two important residues that have been identified are glutamic acid 165 and histidine 95 in this enzyme. So the first thing you want to do is to deprotonate here. This red proton is going to be transferred to the carboxyl group of the side chain of glutamic acid 165. So again, don't stumble on the nomenclature. Glutamic acid is what kind, has what type of side chain? It has negative, but we call it an acidic amino acid. It's an acidic amino acid, but it's functioning as a what? As a general base. All right, don't get hung up on that, okay? Because if it's functioning as a general base, it's going to take a proton on. To take a proton on, it has to have a place to put it, and in this case, it is occurring because the proton has been dissociated to the water. There's a little, I mean, it can become a little confusing because you're going to say the carboxyl group doesn't want the proton. It has low pKa. So why the heck is it taking a proton on during the catalytic mechanism? Because the pKa is with respect to dissociating the proton into water, right? And within an active site, there are other things going on here that's making this proton being able to jump on and off, all right? So this glutamic acid functions as a general base. It takes that proton, and histidine 95 comes into it, and it's in its protonated state, all right? And it is protonating this carbon. So carbon 1 is here, carbon 2 is here, carbon 3 is there. At this point, okay, you have that ene-diol intermediate. What do we mean by that? Okay, this is a it's a double bond between two carbons, and it's a carbene it's a cis diol because it's dihydroxy, diol and cis, they're on the same side. At that point, histidine here, this histidine 95 has lost the proton. Now, going from here to here, the glutamic acid is going to take the proton that it had on it and transfer that to C2. Okay? And this histidine here is going to take a proton from here. So it donated a proton, and now here at the end, it takes one back. The glutamic acid initially took one on and gives it back. So the net result is this transfer. So two important things. It's a classic example of general acid-base catalysis, three important things. One, remember, for something to function as a general acid, it has to be in the deprotonated state. I'm sorry, for it to function as a general base, it has to be in the deprotonated state. For it to function as a general acid, it has to be in the protonated state, because it has to have the proton on it for it to be able to donate it during the catalytic step. Okay, so just the structure of this, it's a beta barrel surrounded by these alpha helices. The important thing about TPI is it's a near perfect enzyme. And you can see, or at least rationalize that in a couple of ways. First of all, how do we know what the efficiency of an enzyme is? We talked about Kcat over Km. Takes into account binding affinity as well as the catalytic transformation. So what did we say the maximum was? About 10 to the 9th. That would be just by diffusion. If the enzyme, just by diffusion, as soon as it hits its substrate, boom, it's transformed. So it's only limited by diffusion. That gives you a theoretical maximum kcat over km of 10 to the 9th, and this is 2.4 by 10 to the 8th, which is pretty astounding. You're only 5-fold, 4-fold off. These are the key residues, all right? Here's an example where when we talk about amino acid substitutions, you say which of these would likely have the least dramatic effect, yada, yada, yada. Most of the time, if you have a glutamic acid and by site-directed mutagenesis you convert it to an aspartic acid, it's a conservative change. There are two residues that are very much the same flavor, very much the same properties, and a lot of times you won't see any change in the activity of an enzyme, right? In this case, if you take this glutamic acid and you convert it to an aspartic acid, kcat over km goes down by 1,000-fold, all right? So that dramatic effect by what is normally otherwise a conservative amino acid change tells you, yes, charge is important, but this enzyme is so perfectly designed that if you mess around even with the spatial arrangement, right, the difference between aspartic acid and glutamic acid is what? The length of the side chain. So if you, even though you have a negative charge there, to carry out that catalytic mechanism where it functions initially as a general base and then later as a general acid, it is the architecture there is perfect. And if you just futz with a little bit by moving that negative charge with the carboxylate back a little bit, you have a 1,000-fold effect. All right. So in all of these cases, you want to be able to appreciate the structure of the enzymes with respect to their function in terms of binding specificity and the catalytic mechanism. Okay? A couple of other things now. So today is Tuesday, right? So on Thursday, we're going to have our last protein lecture, which will be on pyruvate dehydrogenase complex. And that's going to give us, we've gone over this, this is going to give us a little bit more insight to how enzymes use non-protein things, coenzymes or prosthetic groups to do what they have to do. After that, we'll have 4 lectures on membrane structure function before the second exam. Tomorrow, hold on, we got a couple minutes. Recitation. Do you want one tomorrow or not? Well, we're going to have it if anybody wants it. Some people do? Okay, so I didn't post problem set 3 because I figured you did not want to deal with problem set 3 before the exam, which covered problem sets 1 and 2. I could put problem set up 3 today, but we haven't covered all the lectures for problem set 3. So if it's okay with you, maybe tomorrow's recitation, if I have time to do it and you want to do some of the problems quickly, that's fine, but even in recitation, we would only cover them from the lectures we've covered, which aren't all of them anyway. So my thinking is I can show up for recitation and we can simply cover the lectures that have been lectures 9, 10, 11, all right? So then next week, which will be my last week with you, we'll have recitation on Wednesday, which we will cover problem set 3, and I'll put problem set 4 up because we would have covered 2 of the 4 lectures for problem set 4. Then we'll have lectures on Thursday and Friday, and then I have a room scheduled for 3 hours on Friday afternoon I will give you, so that'll be an extra review last day after the last lecture, and we'll cover the rest of problem set 4, and it'll be just open to questions for the exam, all right? No. Is it? Yes. You're right, you're right. So back that up. Recitation will be next Wednesday, normal time. Last lecture, and I have to send you this. I told you we're going to modify, because normally in the syllabus that you got from Dr. Taub, next Thursday was supposed to be a review. And I told you that the last 4 lectures are better covered in 4 lectures rather than 3. Somehow it got condensed. So next week, we will have lecture on Monday. We'll have lecture on Tuesday. We'll have recitation on Wednesday. We will have our last lecture Thursday morning. Then Thursday afternoon, I've got a big room blocked for 3 hours. So we will cover everything there. That'll be the last time you see me talk. And then Friday, you'll have your exam. Okay? I will post that and or send the new syllabus to you by email.
Time for the review?
I have to double check.
On the trips and binding side, right? There's that pocket that